One second.
Oh.
Hi everyone, welcome to the ICTS String seminar. So today we have Victoria Martin from University of Iceland. Will be talking to us about lessons from the quotient structure of spacetime, flat space cosmology edition.
Thank you very much. I'm not used to wearing a microphone, so I'm naturally very loud. So hopefully I'm going to try to whisper, not scream. So thanks for the opportunity to come and speak with you all today. So the first question you might be asking is, why this super long title? Well, the reason is because this is actually the latest edition in a body of work that I've been working on for a little while. And this body of work, we ask the question, suppose we have a quotient manifold like this, where M is some manifold, and then it's quotiented by some discrete subgroup of the isometry group of this manifold. The question we'd like to ask is, what if we knew the generators of this group? What sort of things could we learn? The answer turns out to be a lot. We can learn a lot from the generators alone, including information about quantum corrections. And so this is what this body of work is about. And as you can see, this body of work is taking India by storm. You see, I have two of your citizens here. One, Rahul, is in the audience here, and he's applying soon, so keep that in mind. And Arjun, of course, is normally in Kanpur. And we had initially 07 here, but everyone's traveling, you know how it is. So, but nonetheless, it should be out very soon. Okay, so I'm going to start with a lot of motivational slides, because there's a lot of motivation to be doing these things. So the main idea is the following. Like I said, let's start with some sort of quotient manifold. So by quotient, I mean the geometry that is made out of empty spacetime by identifying parts of that spacetime. So for example, this is the general picture for the BTZ black hole. The BTZ black hole is a very well-known example, so I'll be referring to it a lot as sort of a base case, okay? So for the BTZ black hole, so this is the ADS disk here. These are geodesics, and if you identify a set of these geodesics like this, then you get a quotient manifold, and that turns out to be the BTZ black hole. So this is this is in a picture how you make a BTZ black hole out of empty spacetime. But the BTZ black hole is not the only example. In physics, there are many, many examples of spacetimes that can be written as quotients. So you've got the BTZ, you've got warped ADS black holes, which are interesting, K-boundary wormholes of Hartmann et al., the flat space cosmologies, which I'm going to be discussing with you now, and many more. There are many more examples that I'll be discussing just in future work for this talk. But I wanted to point out that at least for these examples that I've written here, not only are they interesting, but also the group gamma is the simplest group that there is, right? It's just Z. So for this talk, when I have M mod gamma, I'm really going to be talking about gamma isomorphic to Z, but of course we're building up to be doing this formalism for more general gamma. Okay, so as you've probably read now, what can you learn from, if you can compute the generators of this quotient group, what can you learn? You can learn about quasinormal modes, and you can learn about one-loop determinants, for example, not just any one-loop determinant. So for example, I'll be talking about scalar fields in this talk, but this generalizes to higher spin fields, gravitons, fermions, and bosons. This isn't only for scalars, it's just the simplest example. But this REG we see here, we also get information about the regulated part of the one-loop partition function, because usually it has a volume piece. So we get information about all these things that we're very interested in physics for all of these very interesting backgrounds, okay? And how do we do this? The mechanism for finding these things is that we're going to construct a zeta function, okay? Zeta function in general just means that its zeros or poles give you something interesting. These are what zeta functions are. So we're going to compute a Selberg-like zeta function from the quotient generators, And this Selberg zeta function, it turns out to be a cousin of our very famous and beloved Riemann zeta function in a way that I'll explain, okay? And when we do that, once we construct this zeta function, we label its zeros by this S star. And it turns out that these zeros of this zeta function can be mapped to the quasinormal modes. And the zeta function itself can be mapped to the regularized version of this one-loop partition function, okay? So this is the main idea. So now a motivational slide. We can talk about motivation from the point of view of mathematics and physics, right? So this is why mathematicians might be interested in this sort of thing. So for mathematicians, the whole formalism of the Selberg zeta function that I'll introduce and the Selberg trace formula, these only work for a very specific type of quotients, right? Before I had M here, but from a mathematical perspective, what I'm about to describe should only work for hyperbolic quotients like this. And the Selberg trace formula, this is it's a very powerful tool because the Selberg trace formula this is the most schematic version of the formula that you could possibly imagine. This is just a picture really, but just to give you the idea. What it does is it gives you, if you're interested in the spectrum of kinetic operators, which you are, even if you don't know it, because these tell you things about quantum corrections, and they also help in classifying smooth manifolds. So if you want to compute this, which is very hard in general, the trace formula reinterprets the spectrum of this kinetic operator as geometric data on the manifold. So it reinterprets it as a product over these group elements gamma, and this PCC is the primitive conjugacy class, so a special element in gamma. If you don't know this word, this is okay. I'm not going to talk about the trace formula for most of this talk. I only wanted to tell you that the motivation for doing this for more general manifolds is very great because we want to be able to compute these things in general, okay? And so the primitive conjugacy class here, this product is equivalent to a product over primitive geodesics on the spacetime. So, and here's an excellent reference for that. Primitive geodesic, this just means that it's a geodesic that is closed and repeats itself only once. So it doesn't repeat itself. It goes around only once. So this is a primitive geodesic. And this is a beautiful picture in a paper by Krasnov called Holography and Riemann Surfaces of some time ago. And here is this is the example of the BTZ black hole. So what a primitive geodesic looks like on this is you imagine that these two hemispheres are identified, and then there is one geodesic that goes up and down here, and this is an example of a primitive geodesic. So we're going to, by the end of this talk, understand this picture quite well. This is just a motivational slide still, so if it's vague, don't worry, we'll get there. And okay, of course, from the a mathematician might ask, how far can we stretch this formalism? And of course, as you might imagine, mathematicians would be aghast that we're trying to do this just by doing example by example. But it seems like we can. Push this whole trace formula forward a little bit outside of these hyperbolic quotients. Okay, now how about from a physics perspective? By the way, if you have any questions, please stop me. It's okay. Okay, so motivation from a physical perspective. So why don't we quickly discuss different methods that we already know about calculating one-loop partition functions and see where this zeta function fits in, okay? So the first and probably most well-established method of calculating one-loop determinants is the heat kernel method, which people in the audience are experts on. So I won't go in too much detail, but it's important to talk about to understand the relationship to the zeta function method. So the heat kernel method is what I like to call the the take a sad song and make it better method, right? So you have this very hard problem over here. If you wanted to, by brute force, diagonalize this operator, if you were strong enough to do so, then you would get this answer. However, we kind of map it to an easier problem, which is the heat kernel. So this is a heat equation because of the numbers of derivative it has. And there's also boundary conditions that I didn't write down on this slide that the heat kernel satisfies. But so if you can find the heat kernel, then you can calculate the spectrum of this operator by integrating its trace. Okay, and this is a very well-established way of finding one-loop quantities. Okay. So there's a lesser-known method, but still very useful, which is called the quasinormal mode method. So this is by Denef, Hartnell, and Sachdev, about around the same time as these papers that I mentioned up here. And so this method requires really two pieces of intuition. So their main observation was to relate the Euclidean zero modes of the wave equation. So you have some field, like a scalar field, on your manifold. It satisfies a wave equation. And so you relate the Euclidean zero modes, the solutions of this, to the Lorentzian quasinormal modes via Wick rotation. So in this method, you really see this delta, this conformal dimension that's of course related to the mass. You see this as a function, and you tune the delta such that the quasinormal modes are equal to the thermal frequencies omega n, the Matsubara frequencies. These ones are made by requiring regularity in the Euclidean time direction. Okay, so that's the first piece of intuition. The second piece is they use a result from complex analysis called the Weierstrass factorization theorem. So this is that any meromorphic function, meromorphic means that it's allowed to have poles, but the poles are not allowed to accumulate into a branch cut. So any meromorphic function is characterized by its zeros and poles. So they were able to, in a kind of slick way, rewrite, this is the scalar one-loop partition function, this way schematically, where this omega star is the quasinormal modes. Star just is meant to label all other quantum numbers that you might have. That's what star means. Okay. So in a way, this is very nice. It's a bit of a shortcut, but in a way, you see here, you've got some entire function out front. So you are able to calculate the pole structure in this method, but if you want this factor, again, you have to return to the heat kernel expansion to retrieve this factor. Okay. So what I'm going to describe in this talk is very closely related to both of these. So you might ask, this one is useful because as soon as you have the quasinormal modes, you no longer really need the heat kernel if you're just interested in this part. But you might ask, how can I find one-loop partition functions if I don't have the heat kernel and I don't have the quasinormal modes? This is basically the entire idea of the program. So let's see, right. So here are those two methods that we already described. And the method that we're going to talk about now is the zeta function from a quotient group. So we can calculate the one-loop partition function without the heat kernel, without the quasinormal modes, just from knowing the generators gamma of the group that we're quotienting. And you don't have to really know much about this now. This is what the Selberg zeta function looks like for the BTZ black hole. K1 and K2 are integers, and A and B are related to the space-time in question. So A and B for the BTZ case, these are just R plus and R minus. These are the horizons of the BTZ black hole. Okay, and S is the argument of the function. And from the zeros of this, we can map these to quasinormal modes. Okay, tell me. Delta star, yeah, so the n is the thermal integer, and the star could be related to the other quantum numbers. So basically let's see. So you're interested in a solution to this wave equation such that it's regular at the horizon, it's smooth, and so you're going to have a lot of quantum numbers that come into play. You're going to have the thermal integer, and you're going to have other quantum numbers, radial, angular, like this. Yeah, good question. Any other questions?
Something that's confusing me.
Yeah.
You have this formula. Maybe if you go to the zeta function formula, which seems to depend on these two numbers, A and B. But surely it must depend on some data about the manifold n, which is more than these two numbers.
Data from the manifold, right? So A and B are certainly such data points. Like they describe where you put the horizons, where you make the quotient in the first place.
Surely the manifold M has much more data than just two numbers.
So yes, okay, so let's see. Right, so the way I can say, the way this zeta function in the BTZ case, the way that it's defined is it was initially made such that it's a function such that its zeros are mapped to the poles of a scattering matrix. So Perry and Williams are the people who came up with this, the mathematicians, and what they originally did is they were interested in the scattering problem. So they took the Laplacian on the manifold, which includes information about the manifold, right? And they turned it into a 1D scattering problem.
Maybe I think Subrat is asking, this is the zeta function for the BTZ.
Yes, this is specific.
If you view that as some H3 mod gamma, then the information about the manifold is essentially in gamma, the subgroup that you quotient by. So, and that can be effectively translated into those two integers because there's some subgroup of SL2.
No, I understand for the BTZ.
This is, I think, all the BTZ.
This is, yeah.
This is just for the BTZ.
So in general, the formula would be much more. This is only for the BTZ.
Only for
yeah. So we're gonna see later a more generalized version of this formula. So maybe then we can get to your question. Yeah. Other questions? Okay, so it's helpful to know what sort of spacetimes this method I'm about to describe has been done for. So BTZ black hole, of course, this was the very first thing that we did with Andy Fesko and Cindy Keeler. This also works for higher dimensional quotients. We were somehow restricted to odd dimensions. I can't recall why that is, I'm sorry, it was a little while ago. We also did this for lens space quotients, although there were a lot of things that we didn't know at the time. So this paper is probably a little bit out of date right now, but it's useful that it exists at least as a starting point. And then with Rahul and Agla Thorarinsdottir at Iceland, this is the time that we finally generalize this formalism beyond hyperbolic quotients. So this also works for warped ADS3 black holes, turns out. So that turns out, I'll talk a little bit about that turns out to be useful. And so you see that this flat space cosmology with Arjun and friends, this is the 5th volume in this. And it might look like these 3 other books are empty, but to me, these are not empty, of course. I know what goes there. It hasn't been done yet. But for example, there's probably a connection to these recently proposed Wilson spools, if you know. This is a work by Alejandra Castro, Konen, I think, Joanna Komen, Claire Zukowski, and Jackson Fliss. So these Wilson spools are constructed in like a de Sitter or a Chern-Simons representation of quantum gravity. So there are actually a lot of overlaps with this formalism that Claire and I and friends are trying to work out. So we're excited. This he is holographic entanglement entropy is another avenue where these sorts of quotient spacetimes come up. And it's so cool that I'll just take a second to draw it for you, right? So when we're talking about, say, Rényi entropies, we can start off with like a a 2D CFT. And suppose we are interested in two intervals, right? And we want the entanglement. So this is region A, say, and this is B in the normal way. So we want to calculate the entanglement entropy. We use the Rényi entropy trick, which is we make several copies of these guys. Okay? Then through uniformization, we glue these together. And then this becomes a higher genus Riemann surface. So this is C mod some gamma, right? And it's hard to see, but this one in this case is a 2 torus. These are the 2 holes of the 2 torus. And holographically, there's a theorem that says that when you quotient the CFT side, the bulk inherits that same quotient. So holographically, the bulk, the Euclidean version is H3, or yes, H3 in this case, mod gamma, okay? So back in the day, we were very interested in calculating quantum corrections to holographic entanglement entropy. And we were trying to do this from the CFT side by finding generators of this group gamma. But we could only do it in like expansions and small cross ratio. So eventually, what I'm working with also right now with a master's student, but it's a hard program, so I would appreciate any help. Eventually, I want to try to calculate these generators from the bulk side and see if we can make progress with this quantum corrections to holographic entanglement entropy. So this is one future direction. And then warped heat kernels are a natural extension, I guess, of this work, if they don't exist already in the literature. So these are other future directions. Okay. But without further ado, I can tell you what we're going to be talking about for the rest of the talk. So the outline for the rest of the talk, as promised, we're going to start with the BTZ example because this is well known, and this is the first thing that we did. Then I'm finally going to tell you what this zeta function is, and I'm going to tell you how to build it, okay? I'm going to do a quick interlude on warped ADS so you can see how this zeta function changes for a different spacetime. Then I'll tell you what a flat space cosmology is. We'll look at the flat space cosmology results, and then I'll flash a slide about future directions because I've already kind of told you future directions a little bit. Okay. So part one. So we've already seen this little map. You can make a BTZ black hole by identifying parts of that spacetime. In terms of the metric, this looks like, here's the metric for the Poincare patch for ADS. And then doing a series of coordinate transformations, you can get the BTZ black hole, where I haven't written the form of the lapse and the shift, but these are not that important to know. And one such coordinate transformation looks like this. This coordinate transformation, this is only valid for R greater than R plus, okay? If you could get from here to here with just a coordinate transformation, it would mean it's the same space-time, right? So the thing that makes the horizons of the BTZ black hole is that you have one of these for outside of R plus, one of these for between the horizons, and one of these for below R minus. So this is what gives you the horizon structure. And these are sometimes called conformal coordinates in the hidden conformal symmetry language because they take you from this ADS patch to the BTZ. So I'm not going to tell you what this F is because it's not important, but this is one coordinate transformation that does this. Okay. And from the point of view of this metric, what is the quotient that builds BTZ? Well, a priori, this d phi, it could be anything. We're used to it being periodically identified, but in principle, it could be any value. So the thing that makes it a quotient is you define phi up to 2 pi every n times, in a normal way, right? So this is the quotient, and this turns out to have a group theoretic interpretation that is better seen on the next slide. In fact, I'll go to the next slide because it's better seen there. So you take phi, you say phi goes to phi plus 2 pi. What then happens to this coordinate transformation? How does it change? Okay, and you can kind of see how it changes, right? Because in both in the x, y, z, you know that you have this exponential, so you can kind of see with your eye that one of the changes is there's going to be a dilation, right? And even though I haven't told you what this function f is, you can believe me that the other function, there's also going to be a rotation involved. Okay, so this is a group theoretic interpretation of the quotient. There is a dilation that's given by r plus, and there is a twist or rotation that's given by r minus. This absolute value is because this is for the Euclidean case. Sometimes I'll switch to Lorentzian, but I'll try to make it I'll try to make it clear when I do that. Okay, so the group generator of this quotient is there's some amount that's in the rotation and some amount some amount that's in the dilation, some amount that's in the rotation, right? So this very jazzy picture that I had in the beginning actually has something to do with this talk, right? So this is pictorially giving you this vector field. So there's a dilation and a twist, okay? So that's what this is. Right, so d phi is z. So, right, like it looks like a U1, right? So, but really you can think of it as z. So you're identifying every 2 pi. Yeah, so. The pi is just for, I hate this pi, but it's just for like a normalization thing. It doesn't mean anything. That's the group element. The group. So this is the generator, and you can exponentiate it to make the group element, but it is discrete because you just go around the every 2 pi, if that makes sense. No.
It's not a loop. So how can I exponentiate the generator? Discrete group generator is supposed to be a group element.
Right.
Gamma is the
Gamma is the exponential of that.
Right, that's right.
Gamma is a particular element. Okay. One element of the group.
And there is only one.
By the gamma
I
to be.
think the next question is gamma equal? How is that related to this boxed pi here?
That's the generator, yeah, of which e to the
Yeah.
e to the back.
Okay, that's
Yeah.
There is an underlying group, but you take discrete subgroup of that.
Yeah.
Mm-hmm.
It's a subgroup.
Good. Excellent. Any other questions? Okay. Okay, so this is the thing that is going to help us build the zeta function that I'm about to describe to you. But now I first have to tell you what the zeta function is, but the important data is in this box, okay? So what do we have? So let's see. Okay, so fun with zeta functions. So the most famous example of a zeta function that you might know is the Riemann zeta function. So we are going to be more interested in this in the way that Euler was, which is this unsupposing series, this unsupposing summation, actually turns out to give us information about the distribution of prime numbers. Turns out. The Selberg zeta function is a direct cousin of this one, except you replace prime numbers with prime geodesics on the manifold. The prime geodesics are the ones that are closed and don't repeat. Okay, so here is a very schematic example of what this would look like. So n of p is a function of the length of the prime geodesic. So that goes here. This can also be written as a group element. so a product over group elements if you have them. And this n, the integer that appears here, has to do with the number of dimensions you're in, right? So there's only one integer here, so we're in 2 dimensions. This is actually for a disk. But in higher dimensions, we have 2 integers. The BTZ black hole had K1 and K2, so it's 3 higher dimensions that goes like this, okay? So this is a schematic representation, and now we can just look and get a little bit more flavor for this picture, because why did I write this geodesic particularly, or why did Krasnov? Well, it's because this is the line that you can see is invariant under a dilation and a twist, right? So this tells us that this particular one is the geodesic that we should be interested in. Okay.
Yeah, higher dimension is you have more integers than 1 and 2.
Yeah.
You have more functions, capital N also.
No. It'll be the integers, yeah, no. It'll just appear up here. What you have, when you have a product for n, that's actually more with the group elements. But we actually, for our purposes, we never see this product because our group is always z. So we only have 1 element, so that product is gone.
What's the definition precisely of prime geodesic?
Right, so it's a geodesic that it repeats itself, so it's closed and does so only 1 time.
So if I draw a line like somewhere to the right of that line, it's also better for the outside.
Right, so then what would happen? Yeah, exactly. So then what would happen? So then you draw it here, right? And so, but I want this picture to be invariant under a twist and a dilation, right? So what it's going to do is this is going to come out someplace over here, and maybe it won't repeat in a nice way. This one, though, will. Yeah.
And in what sense are they prime? Is there a sense in which all geodesics can be generated by somehow combining these prime geodesics?
Yeah, I think so. These prime geodesics, in a group theoretical sense, they're related to these like primitive conjugacy classes. So you take a product over those, and then you can somehow take a product maybe over other quantum numbers to get the full group. So these are related to the, it's in the sort of textbook that I showed by Gutzwiller. He kind of discusses how these geodesics are related to the primitive conjugacy classes thing with the group. So yeah. Other questions? Okay. And so I want to put one thing to point out is that the zeta function is also a meromorphic function on the complex plane. So this is actually one reason why it's a little bit weird. So I'm about to tell you at the end of this talk that this formalism goes through for flat space. And this is a little strange because in flat space, poles tend to accumulate into branch cuts. Nonetheless, we see that if we take limits carefully, it still goes through and we reproduce known results. So.
From the hyperbolic case, it's not obvious. Right?
Yeah.
Statement that it's a meromorphic.
Right, that's right. Yeah, exactly. Good. Questions? Okay. What is next? Okay, so now I've shown you this a little bit. Last slide, so this is the Selberg zeta function for the BTZ. Before there was an A and B up here, but these are related to the modular parameter on the torus. BTZ is a torus, so it has a real part and an imaginary part. They turn out to be related in this way. We've already found that this is the quotient that we're interested in. Just so you know, like for those of you who are super used to heat kernels and things, there's another way to rewrite this. You can see that by introducing this Q object, that the zeta function takes a somewhat more familiar form here, and we're going to interpret this later on in the talk. So mathematicians, it turns out, calls this the gnome, which I think is a very oh shoot, hold on. never mind, I don't think it's cute anymore. No, so this is called the gnome. Actually, the gnome is slightly different spelling. Actually, the gnome is usually defined without this too. So this is the gnome squared. Okay, so now how does this work? So this is the Selberg zeta function for the BTZ black hole. We're interested in its zeros. We know where those zeros occur, right? Because it's an exponential. So this function ought to have zeros every time the exponent is 2 pi I times an integer, right? That's where the zeros occur. And the mechanism is that if we tune the zeros of this zeta function to the conformal dimension of the field in question, that is an equivalent statement to tuning the quasinormal modes to the Matsubara frequencies. Okay, so this procedure gives you, if you have any 3 of these, if you have knowledge of any 3 of these, you get the 4th one for free. So this is can be seen as a means of predicting quasinormal modes for a given spacetime, given quotient spacetime. And it turns out, for the BTZ black hole, for the scalar one-loop determinant, it's the zeta function with this argument is mapped directly to the regularized version of the determinant. So, regulated version. So probably this Selberg zeta technique is assuming some sort of regularization technique in the first place, probably zeta function regularization. But it's nice that it already gives you the regulated part, so you don't have to go through the trouble of taking care of the volume piece. Okay, so this is the structure of the BTZ, and we're going to see how it goes through for other spacetimes now. Okay, let's see. Oh, yeah, tell me. Yeah.
You said something earlier that the zeros of the zeta function relates to the pole of the scattering matrix. Order matters, order of the pole. Order of the pole in the scattering matrix is also related to the order of the zero.
Right. So the poles of the scattering matrix are related to the quasinormal modes. So that's why we kind of want the zeta function. It wants to have zeros that are mapped to those poles. Is that answer your?
That's about poles, but there are to each pole there is some order associated to it.
Oh yeah, that's right. There are some like degeneracies. Yes.
So that is also correspondingly similar in both cases. In zeta function, you can say that about what order of pole is there in the scattering matrix.
Yeah, good question. So, good question. Yeah, I think indeed there is a way to see what the order of the pole is, but I will have to think about. I think that this is ringing a bell for when I did like the higher spin ones, but I'll have to look back. This is a good question. I'll see it. I'll see you again. Yeah. Other questions? Okay. Oh. Okay. So right. So how does this mechanism take place? Well, it turns out that these integers that appear in the zeta function, these integers are mapped to the quantum numbers that occur in the quasinormal modes. So it turns out that K1 plus K2, this is mapped to the radial quantum number. This one is mapped to the thermal quantum number. And this L that comes from finding the zeros in the first place, this is mapped to the angular quantum number for the BTZ black hole. And this comes from the scattering argument. Yeah. So this comes from the scattering argument of the BTZ black hole, but we actually take this as it is and try to push forward for more general cases. Okay. Right, so a word about generators. So to extract the Selberg zeta function parameters, the A and the B, we use the embedding generators, these which we've labeled J12 and J03. So here is the embedding metric with this constraint, and to the Poincare metric, you can find this this coordinate transformation. And so these are the ones that we're interested in with isometry group SL2R cross SL2R. Okay, and it turns out that the generators that these are interested in, we can already see from here. We've got the dilation and the rotation here. So it's only the zero generators that appear in the quotient. And this turns out to be kind of important for the warped case when one of these is broken down to U1. Okay, so this is just a word about generators. We'll talk about generators a little bit more. So I only have 2 slides for the warped case. I have backup slides if anybody wants to discuss. I'm only going to say the results and move on just to show you what sort of different things happen. So it turns out that warped ADS3, this is a metric for warped ADS3 in global fibered coordinates. This nu is a warp factor. So if you put nu squared equal to 1, then you get back just regular ADS3. And these folks, they showed us that this space-time is also that warped ADS3 black holes are also quotients of warped ADS3. And they were kind enough to write down the generator for us. So in terms of these generators, J2 and J2 tilde. It turned out, we didn't realize at first, but it turned out they were in the wrong linear, we needed to take a linear combination of these to get our A and B parameters. But here's what the Selberg zeta function looks like in the warped case. Turns out it looks exactly the same exact form, except that the parameters A and B contain this warp factor. So the exact same zeta function goes along for the ride with us. And what were we able to achieve with this? Well, from this zeta function, using the method I described, we were able to reproduce the quasinormal modes that were calculated in a completely different way by these people. And in this way, we were able to find a candidate for the scalar one-loop partition function for warped ADS3 black holes, which I didn't do the most thorough literature search on, but I wasn't able to find this in the literature already. So even if it does exist, this is another means that the zeta function should be directly related to this, this one-loop partition function. And it's also a proof of concept that this whole Selberg zeta program works outside of hyperbolic spaces. So this, at this level, and for this project, we did not compute this. This one we just took, and it reproduced the quasi-normal modes, it turned out. We didn't need to, but I can show you, but it turns out that when I'm about to tell you in like 1 or 2 slides, I'm about to give you like a sort of general definition for what this is, or at least a proposal for manifolds like M mod Z. And from there, we can kind of see what this is meant to be. So we didn't actually compute this because we didn't really understand how, but now we can. Yeah?
So just to understand, the magic is actually that when you look at the quasi-normal modes,
yeah,
which were already computed by Stromage and all, that you find that they are the same as the VTZ quasi-normal modes, provided we change some parameters in the space.
Right. Provided we identify some of these integers with the quasi-normal mode.
So this is an observation that just follows at the level of quasi-normal modes, and now you're saying you can relate this because you know quasi-normal modes are related to Selberg zeta function. You're saying Selberg zeta function. Is that, am I understanding?
Yes, that's right. That's right. So this is true. So at least, so this is true, right? So this is true at the level of quasi-normal modes. But because this is a limit, because the warped case is kind of a limit of the ADS case, we do expect that not only do we get the quasi-normal modes, but we also get the one-loop scalar partition function. But we haven't shown this. This is just a candidate.
What does it mean that to reproduce the quasi-normal modes for the black holes? I thought that was what went into this Selberg zeta function.
No, it could be an input, but need not be. The inputs are 4 things. The inputs are the zeros of the, which depend on A, B, it depends on your space-time parameters. the thermal frequencies are an input. The conformal weight is an input, and quasinormal modes. So if you want to compute any of these, suppose I want to compute this one, then these are the inputs I need.
To compute the Selberg zeta function, you used data about the quasinormal.
No, about the quotient.
About the quotient.
Yes, about the quotient only, and that's the entire thing.
Quotient is still of the form aj12 plus bj03, but the a and b is what we
I see. Also, the fact that I see. So now, so the fact that the original manifold was in fact of ADS, you're saying does not matter in the zeta function.
It turns out, yeah, the form of the zeta function is exactly the same.
So, but how do you know that? Are you just putting it? Something?
Yeah, we don't know that. We do not know that at this level. So at this level, we just tried something. It reproduced the correct quasinormal modes. By Denef, Hartnell, and Sachdev, that actually kind of means that it must be in part related to the zeta, to the one loop partition function.
So knowing A and B is not in general sufficient to know the zeta function, but you guess that it would be.
Yes, we just did whatever, we just did the simplest thing. Yeah, and it works. Sometimes it works, you know. So, but now we're gonna talk about a more general thing.
Judging from this form, that the fact that this form is the same as the BTZ, you only have one prime geodesic two, and the difference in parameters only show up in the length of the geodesic.
That's right.
That's why it's the same.
That's correct. Yeah, that's right. Very good. Other questions?
So also for warped ADS, it's basically one of the SO2Rs is breaking 21. So really the two generators there, one of them is from the SO2R, the other one is the one generator which is left after break. So luckily.
Yes, exactly. Okay. In fact, we did do, let me see if I can go back a little bit. So we did do an entire rigmarole of how to find the linear combinations of these that we needed, which involved like a warped, we had to like build a warped version of the ADS Poincare patch, which didn't exist in the literature. I have backup slides for that. I won't discuss it though. But it was a wild ride, but it was very fun. And
are you saying that to identify the quotient was what required this node? When you say you did this change of basis, what does that really mean?
The change of basis. Oh, what I just said. Oh, yeah, sorry, change of basis. Yeah, exactly. So the name of this game was to take whatever worked for the BTZ black hole and try to do the same thing. So here, we wanted to write these in terms of the embedding generators because the embedding generators are giving us the correct A and B, if you like, right? But there is no embedding for warped ADS. So we had to go through this kind of process to find the correct linear combination of generators, if you like, which is L naught plus L bar and L naught minus L bar is the linear combination I'm talking about. Hopefully we'll see this more in subsequent slides. Okay, good. So that is it for the warped case, but we can discuss later. Now flat space cosmologies, okay? So these people showed that flat space cosmology is actually a solution, can be embedded in string theory. And so what it is the following. So it's easiest to see, you can make it in its own right as a quotient of flat space, but just for the purpose of this talk, it's easiest to see as a limit of the BTZ black hole. So this is the BTZ metric written in a different way, okay? And you can get flat space cosmology from taking a limit of the BTZ black hole. So you take this kind of funny limit where your R plus, your outer horizon, should be scaled with L, and this dimensionless R plus hat, which is related to, square root of G 8m. And R minus just scales as this dimension full, R naught. It turns out that dimension full is not a word, but I wrote it anyway, we use it, okay? So, and we are taking the flat space limit. So we want to take this dimensionless limit. So these dimensions work out in 3 dimensions. This is dimensionless. And we want to take this going to 0. The fact that this parameter is dimensionless, this R plus hat, and this is dimension full, turns out to cause a few problems. There's some hijinks, not problems, just a little hijinks. So we'll just have to keep that in mind. And this is the metric that you get for flat space cosmologies. It's just this one. So what happens? So now the radial coordinate, for example, is now time-like. So it's got this minus sign out here. And so what we have instead are like a time-like horizon. And this is why it's called a cosmology. Right, so these are in pictures. We start out with the BTZ black hole that has an inner and outer horizon, okay, in the radial direction. And we're essentially pushing the outer horizon way out. So we're inside the black hole now, if you like. And now, but we've switched also to time-like horizons. So we have one horizon and it's a cosmological horizon, it's time-like, okay? So the motivation for this project was Arjun was like, oh, there are these very weird boundary conditions that you need to calculate quasinormal modes on this space-time. Maybe we can use the Selberg formalism. And it turns out to be working pretty well. There's still just a couple things left to do, but it's working pretty well. So yes, these are the pictures. Okay. We can also talk about the generators. Yes, we can also talk about the generators of, the asymptotic symmetry algebra of flat space cosmologies. So for ADS3, as we all know, the asymptotic symmetry algebra, that one forms 2 copies of Virasoro. So the curly L's are meant to be the Virasoro ones, and these flat L and M's are meant to be the flat ones.
The Selberg formula is working well. Are you going to explain that more?
Yes, I'm going to explain it in detail. Yeah, I'm going to explain it in detail. So here are the 2 asymptotic symmetry algebras for this for these flat space quotient. It turns out to be BMS3, and you can get these generators. You can get one from the other in the following way. So you can get the L's as a linear combination of the Virasoro L's here. You can get the M's in this way, where now you have to scale with this epsilon. So this is part of the hijinks of the dimensionless dimension full thing. And here are the representations labeling the BMS. So we have J here for spin, and we have M here for the mass. And this gets an epsilon too, by virtue of this guy. Okay. So now what is flat space cosmology as a quotient in its own right? So here's the again, it's going to be as a limit, but here's the BTZ example, everything that we have to know about that. Here's the limit that we've already discussed. And what happens now? So now, what generators are going to make up the quotient? Again, it's going to be the 0 generators, L0 and M0. And you see, if we carefully take this limit, our dilation and rotation become a boost and a translation. So you can think of taking these, the radii, for example, of these 2 hemispheres out to infinity, you get something that looks like this. Okay, so there is a translation and there is a boost. This leads some people to call these spacetimes shifted boost orbifolds, which, okay, you can do. You can also call BTZ black hole a dilation boost orbifold, but then no one will want to sit next to you at lunchtime. So don't do that. But another thing to notice is that this generator is dimensionless, and this combination is dimension full, okay? We go along with this. And we can get what this generator is as a limit from the BTZ case. So this is the one from the BTZ case. And we can take these limits in turn. So A, which is related to r plus hat, can just go through like this. There are really no problems here, no hijinks happening. No, we get this for the J12 generator. For the J03, you have to do it in 2 steps to make sure everything stays finite. So you multiply and divide by L, and then you can take the limit, and it looks like this. So for the flat space, you again, the quotient is again given by the 0 generators, and these eta and rho parameters are defined like this. So now we've absorbed the G into the rho, so that now everything is dimensionless, just like in the BTZ case, which is what we like. Okay. All right, now let's build the zeta function for this thing. Okay, so here is a proposal for like a generalized Selberg zeta function for a general quotient M3 mod Z. So this works for all of the examples that we've tried so far, including the flat space, cosmologies. So I'll go ahead and, this is a proposal, but so far it works. Okay, so what you really need here is you want what you probably could have guessed, this exponential argument as an operator, you want 2 pi I d phi. That is to say you want the group element, right? And the product, you can engineer to be a product over descendants. And the expectation value is over the scalar primary of weight S. So for this entire slide is for the BTZ case. So let's see how that works. So for example, you can label a primary state like this, and then the highest weight representation, and then descendants are labeled in the following way, where K1 and K2 are the number of applications of this operator. And then you can go ahead and write the BTZ, you can write this group element in a way that we've already found. We already found this. In terms of this gnome, it's as an operator, it looks like this. So very familiar from a CFT perspective. And right, and so you can find these eigenvalues. These are the eigenvalues for L naught and L naught bar. This delta, so H is equal to delta over 2. And this is a scalar field, so H and H bar are the same. And so just the last thing to remember is that this is some S, but we're going to want to identify this S with whatever mass parameter we've got going on here. So for the flat space case, this is just M. This is just little m. So here is a proposal, and we can see how this works. So this turns out, so we can put this all together, just do a little bit of algebra. Indeed, this recovers a Selberg zeta function for the BTZ case, and we can kind of immediately see how this would generalize to different groups gamma and to higher dimensions, kind of like we've already described. So higher dimensions, it would just be more integers here, okay? And a more general gamma, then we would have to take a product over these generators. So we already have a very schematic proposal for the more general case, but of course we learn best by example, which we haven't done yet. So there is this. And so what do you get for the Selberg zeta function for the flat space cosmology? Okay, so you get exactly this. So starting with the zeta function out here, you can, in terms of the BMS generators, you can write out the group element, and a primary field of mass M and its descendants can be expressed here in terms of K1 and K2.
When you say product over descendants, is that basis independent? Descendants you could write different bases. I thought it was important in this GCA story that you took a particular combination of L0 and L0 bar.
Yeah, that's right.
So when you say product over descendants,
You kind of, yeah. This is a good question. We kind of do fix a basis. It's the basis such that the descendant labels are going to give us the same sort of labels that give us the quasinormal mode quantum numbers.
so I mean, I could have used L minus 1 plus L bar minus 1.
You could call this like, yeah, you could call this anything. Like you could call this a J, for example.
Then the formula depends on the basis, then I'm a little confused. Why is that?
Yeah, so I think that one thing to say, right, yeah, so this is, I think, potentially basis dependent at this point, although it's not written here. We just, wouldn't you, do you agree, Rahul?
I think basis is kind of fixed by how you can recover like the d5.
Right, so it's in a sense, yeah, so we kind of knew, we kind of know what is meant to go up here, just some sort of, we didn't really have to call it this, we didn't have to say L0 minus L0 bar up there, but it turns out that that is the combination, the dilation and the twist sort of argument. So we take the quotient, we see what it's made out of. For the flat space case, it's the boost, and it's the translation. We take that and we see how much of each of those go into the quotient. And then we build this Zeta function here. In terms of this grouping, this sort of grouping is from the generators, I guess, of this quotient. This boost and this twist kind of fixes that.
I think maybe a basis independent way to think of it as because it is some kind of a determinant, and you're evaluating the determinant on a basis in which it's diagonal. So you take the highest weight and then you diagonalize the generator that you are evaluating the determinant. You're evaluating the determinant of some group element. And that element you diagonalize on the basis.
I really think it's just the determinant. That would be some.
Always what we're doing is calculating like the determinant of a kinetic operator. I say partition function just because in the scalar case they're directly related, but always we're calculating this determinant, yeah. All right. Okay. It looks fine on this.
Might be the connection to the cable. Maybe the cable is coming loose.
Yeah, don't know. Oh. Yeah, I'm not going to touch this because I'm allergic to yeah, but so I can, while this is happening, I can say a few more things. So in order, oh, it's kind of.
Yeah, I think they're coming.
Yeah, they're coming. Anyway, I can say a few more things. So behind this, you know, we calculated some zeta function, right? Okay, big deal. Like, how do you know it's anything at all? Okay. Well, it turns there are two checks that we can do to see that it's right. It turns out, happily, that a group of people actually computed the one loop partition function for scalar fields on these flat space cosmology backgrounds, and we recover it, so we get the same thing. So this is like a non-trivial check that this is working in the flat space case. So this is. Yeah, so this is exciting.
How did they compute this?
By the heat kernel, by the heat kernel, exactly.
And since these geometries are limits of BTZ by taking some flat space, can't we just take the answers for BTZ and just take the limit inside those answers?
Yeah, yes, you can. But so, and in fact, you can check as well. So there are two checks. One check is from the partition function that was computed by others. One check is to take the limit of the BTZ and see that you get the same thing. You can do that, the limit's a little bit tricky because of the different scalings that come up. So there has to be care taken, but yeah, you can do it. We just had to figure out how to do it. But it's important, like, this was very nice because this space-time was nice because we could take a limit of BTZ and get something, and then we could find a way to compute in the more general case, and this allowed us to get like a proposition just from the quotient alone. So this one doesn't take a limit at all. So
how does it actually solve the wave function, the wave equation in these times?
how, you're right, exactly.
Because it might not be very hard to just directly solve the wave equation obtained on the eigenvalue.
Yeah, so yeah, it's not so to calculate this thing in BTZ, it's not from the, yes, no, it's not hard. For the BTZ, it's not hard because you can just use the, like, it breaks up the Laplacian as a very nice form. It's this like Posh-Teller potential that it turns into, and things are known. But in the warped case, it's maybe not so nice. So this is kind of a way to get around that.
And in this flat space cosmology case,
In the flat space cosmology case, at least for the one loop partition function, they didn't, that group didn't seem to have a hard time doing it with the heat kernel. So it's not like saving anything there, but it's just, this project is to do two things: to show that it works in the unlikely case of the flat case. It was very unlikely that something like this would go through, but it does. And also, in calculating the quasinormal modes in a direct way is a little bit strange because the boundary conditions of the spacetime are a little strange. So the quasinormal modes for the spacetime have not been computed. We have a proposal for them that I hope to get to, up to an undetermined function. And Arjun and collaborators are also doing the same computation now, attempting to do so from the torus 2-point function. Okay, so we'll be able to. We don't match right now, which is why I couldn't put 07 on the title slide. Good. Okay, any questions? Sorry, I know I'm going a little over. I will speed up. There's not more. Just to say that this just, once you calculate the flat space one, this actually makes some sense from the case of the quasinormal mode quantum numbers. Because, so in the BTZ case, there was also a K1 plus K2 here. And that one was associated to the radial quantum number. The fact that it's not there makes sense because now our horizon is time-like, right? So usually when you calculate quasinormal modes, you have to do boundary conditions at the radial horizon. We don't do that, so we don't have a radial quantum number now, just as we would expect. So this is very nice. Right. I've already described this slide to you, so I don't really need to do very much. This is the check one. So this group here has calculated the one loop partition function already via the heat kernel method. This is what it is. And it turns out that we can recover the Selberg Zeta function that we got. The algebra for this is not very hard. I would never put algebra like this on a slide, but it's super easy. It's just the expansion of like log is a power series and then like geometric series that you sum, and voila, you get the right answer. Okay, so that's one check. The other check is you can do a limit from the BTZ case and you get the right answer. I can talk about that if you like. And now what do we do with the quasi-normal modes? The quasi-normal modes, we're still kind of in the process of calculating. So now the background of these slides are going to change. So now this is scratch paper now, okay? But to get the quasi-normal modes, we have to calculate the thermal frequencies on this space-time. And we do this in the normal way. We try to do regularity around the time-like horizon. And we get this very reasonable looking quantity. These are the thermal frequencies for the non-rotating BTZ black hole, for example. And then you have this angular part where this temperature in omega can just be calculated from the space-time metric in the usual way.
Sorry, but in a cosmology, what is the meaning of quasinormal?
Yeah, this is a really good question. So you still have a horizon, be it time-like. So you should still have modes that are dissipative in some way. I guess what you could do is you could define quasinormal modes as like even via the scattering problem, right? You have some Laplacian on this space-time, and you can calculate like the scattering resonance, which also
boundary conditions, would they make physical sense? I mean, normally you impose some purely following boundary conditions or something.
Yeah. So this is a bit the crux of the whole problem. We're trying to actually circumvent this issue of trying to do the boundary conditions very carefully because it's very subtle. It is very weird boundary conditions. And so we haven't gotten, and because of this issue, so we're still trying to iron this out, but just from the zeros alone, we get an answer. So this top condition that we always say, you can rewrite this condition as something like this, that we are going to, this ought to be 0, and this ought to be 0, and they're related by some undetermined function q. Usually, like for the BTZ case, we know exactly what q is, because like for the quasinormal modes in that case, you wouldn't want them to involve the thermal integer, for example. So you can choose q so you can choose this so that the thermal integer vanishes. Here in this case, there's no such, here in this case, so far I do not know how to choose q, because what sorts of quantum numbers should you want in a flat space cosmology? It's a little like de Sitter. So you should want an angular quantum number probably. And you're going to want a thermal quantum number for this case because your horizon is time-like. So this is the angular quantum number. Sometimes I called it L. In this case, it's called K. I'm sorry about that. This is M, the mass. This is the thermal integer. And basically, because the zeta function that we built reproduces the one-loop partition function, unless DHS, Denef-Hartnell-Sachdev, unless that somehow breaks for flat space cosmologies, which I can't imagine that it does, in a sense, this has to be correct. Although I don't really know what this one is, and I don't know how to choose it, this Q. So we're kind of working through that. And Arjun and company are working in a different way, so hopefully we can make some progress with this. What is the partition function? It's just, I define the one loop one by, so I'm wanting semi-classical information. So for me, when I say this, it's defined as follows. So for the scalar one loop partition function, maybe this is a little bit too much, but what I'm really calculating is the determinant of the Laplacian on this background raised to some power, depending on whether it's a real scalar field or a complex one. So this is scalar. So really, I call it partition function because I'm talking to physicists, but really this is what I calculate, which is fine to calculate, I think. Yeah, the physical meaning. I mean, I guess I would have to ask you a question then in turn. So what would stop this to have the normal meaning of a partition function? It's just like a, collection, an integral over, states. What breaks in this case? Yeah. Right. Yeah. So, I mean,
easy to understand.
Yeah.
Here, I don't understand.
Okay. Yeah, I mean, maybe I'm being, it's true. So maybe I'm being a little bit too fast here in assigning this, like trying to assign this a physical interpretation in these spacetimes. Really, I'm kind of calculating this like mathematical object. Yeah.
You've done the Euclidean continuation.
I'm sorry, sir?
You've done the Euclidean continuation.
Yeah, so I've kind of gone from Euclidean to Lorentzian a little bit fast, but the reason is because this is very closely related to the DHS method, right? And so that is taking something that's Lorentzian, the quasinormal modes, and it's comparing it to something that's Euclidean, like the zero modes.
In terms of definition, you're saying this is done after you've done the Euclidean continuation.
So building the zeta function, like you can do it in the Lorentzian case and the Euclidean case. You don't really need to, you don't have to worry so much about Euclideanization. You did from a mathematical point of view when you were just doing the hyperbolic quotients, right? Then you had to be really careful to Euclideanize, allegedly. Here you can calculate the zeta function in a non-Euclidean setting, and it just turns out that some things change. Like B Euclidean is something like it's something like this in the Lorentzian case. This is the Euclidean one. In the Lorentzian case, it's something like this.
The right boundary conditions put in the horizons. Because if you just computed the determinant of the wave of the Laplacian,
Yeah.
for the Lorentzian black hole, it would be continuous. Maybe after you put infalling boundary conditions, you get a quasinormal mode. So that's what you mean, like you want to compute that of this Lorentzian operator with the right boundary conditions put in.
Yes. Let's see. I'm trying to think about where the boundary conditions actually do come in, because I guess in the only boundary I guess that you kind of care about is like the boundary. So it's a quotient, right? So you have like, you're just always in like one fundamental domain, if you like.
The Euclidean case you don't care about it because the geometry caps off at the horizon.
Mm.
The Lorentzian case you do care about it because the horizon is not a point. Okay? The horizon exists, and you have to impose ingoing boundary conditions to get some discrete spectrum. I suppose you're assuming that you've done that somehow.
Yeah, in the BTZ, I think that's what you take a Euclidean one with regular boundary conditions, and that translates to in following boundary conditions. And in the cosmology case, that's what I guess.
Exactly.
Especially because you have that horizon, which is and it's time line. I mean.
Yeah. So exactly. It was probably not rigorous enough on this point, but really the same thing goes through if you do this in the Euclidean case, and then you can rotate back to Lorentzian signature. So Arjun and company, they did find a way to Euclideanize this. These flat space cosmologies. So we know how to do that. In fact,
are they real metrics in Euclidean space, or are they complex metrics?
I don't remember.
It's real, but they have a spin.
Yeah, you have to complexify one of the parameters as well. I think.
Right. Yeah, I think.
Otherwise,
it's R naught. I think it's complexified. The horizon thing. Yeah. Yes. Okay, this is the last. Let me just make sure. I think this is the last slide. Future directions. Tons of future directions. Hit me up. There's all kinds. So that's it. Okay. Yeah. This one? How do you, I don't know. I mean, it's some, yeah, it's some CFT like calculation, or, I mean, that's where field theory calculation, at least, that I personally have not done. I cannot even tell you because like his thing is not out yet, but there are references. Do you know Rahul, that you can think? Yeah, there are references. I can probably tell you later, but I've never done that myself. Yeah. Okay.
Are there any questions? No, let's thank Victoria once again.
Thanks. Yeah. I know you have to leave immediately.
Sure, but
What do